In 1834, a Scottish engineer named John Scott Russell was watching a barge being towed along a canal in Edinburgh when the barge suddenly stopped. The wave it had been pushing forward didn't stop. It kept going. A single, smooth, rounded heap of water, holding its shape and its speed for miles. Russell followed it on horseback until he lost it around a bend. He spent years trying to explain what he had seen. Most physicists of the time told him he was wrong. Waves of that kind were supposed to disperse and flatten out. Russell insisted the opposite was possible. He was right. What he had discovered was a wave that doesn't spread, doesn't slow down, and doesn't lose its shape. A wave that behaves, in almost every measurable way, like a particle. The phenomenon was controversial for decades. Then, in 1965, Norman Zabusky and Martin Kruskal discovered through computer simulation that these solitary waves could pass through each other without distortion, emerging from collisions with their shapes and speeds completely intact. They named the phenomenon a soliton, borrowing the "on" suffix from protons and electrons, because it behaved less like a wave and more like a particle. Einstein spent the last 30 years of his life searching for a unified field theory and never found one. The concept of the soliton wasn't available to him. It wasn't named, formalized, or understood until a decade after his death. But by that point, work on understanding the ether had practically come to a halt, and the scientists who would have been most likely to grasp the possibilities had passed away. Research had gone in a completely different direction, and virtually none of the succeeding generations of physicists were even looking for it. A soliton isn't a new kind of object. It is a behavior, the behavior of a disturbance that maintains its structure as it moves, because the medium's own nonlinear response prevents it from dispersing. And this is the answer to the question we left open at the end of the last video. If a knot is a deformation in the membrane, how can it move? It moves as a soliton. The knot doesn't carry the same membrane material as it travels. It hands its deformation forward, patch by patch, the way a bump moves through a carpet. Push the bump to the other end of the room, and the carpet under the bump when you started isn't the carpet under the bump when you finish. The deformation traveled, the material didn't. The knot isn't a thing sitting in the membrane, it is a pattern that the membrane is enacting. This distinction matters more than it might seem. It means a knot has no fixed address. It isn't located in any particular patch of membrane any more than a wave on the ocean is located in any particular water molecule. What makes it real, what gives it mass and an electric field and all the other properties we measure, is the topology of the pattern itself. Topology is the branch of mathematics that deals with properties that survive continuous deformation. The number of holes, the number of crossings, the handedness of a twist. Those properties don't change when you move the pattern from one patch of membrane to another. The knot doesn't retain its identity because it is made of specific material, but because its structure can't be smoothed away without an enormous energy input. This is why matter is stable. It isn't composed of particles that are hard little balls that resist being broken apart, but of patterns that can't be undone without more energy than virtually anything in ordinary experience can supply. In the next video, we will discuss elements and their formation.